Okay, in this video, we are going to talk about the IT 3206, which is the data structures and algorithm. We are going to specifically look at the trees data structure, right? Okay. So, what is a tree? So a tree, it's a hierarchical data structure, meaning you have a parent and a child relationship. So that is what is meant by hierarchical data structure, right? Here also we have a parent and a child relationship. Consists of nodes connected by edges. So we have two specific terminologies here, nodes and edges. So in a tree like this, so this is one of these is called a node, and the nodes are connected with edges. So these are called edges. This is an edge, right? So this is like specific terminology we have here for the tree data structure. So we have nodes and then we have edges. So we have some rules here. For trees, every item in the tree is a node. So this is a node, this is a node, this is a node, right? The node at the top of the tree is called a root. So this guy is called a root. This guy is called the root. So that's basically for a tree you have only one root, right? So that is the top of the tree, and every non-root node has one and only one parent. So if you take this guy, this has only one parent, right? So 15. So if you take 18, it has only one parent, which is 4, right? So each non-root node, you have one parent for each of those nodes, right? Okay. And then a leaf node has no children. So here on the last level, we have the leaf nodes. So as you can see, they have no children, right? So these guys have no children, so we call them these are all leaf nodes. We call them the leaf node, right? When you have multiples of them, they are called leaf nodes. All right. Okay, so each node can have multiple children, as you can see. So this guy can have multiple children. This 4 has 3 children here, 9, 18 and 3. When items contain other items, or items can descend from other items, trees can be a good candidate to represent it. So tree is a data structure. So ultimately what you're going to do is to represent data in the computer, right? So in a logical sense, this is when you have hierarchical data, tree is the data structure to go for, right? So here are examples. We have this file system, right? In Windows Explorer, you have the folders. Within the folders, you can have multiple nested folders, and as well as you can have files. So that is basically a hierarchical data structure. And then for Java, you have class hierarchies, right? So there could be a common class called object, and then you have specific classes like exceptions, and then from there you have specific exceptions, right? So there's a hierarchy of classes. So that is also a good application of the tree. So these are the things that we already discussed. This is root node, this is an edge, and then the last node, which doesn't have any any children, so no children here, this is called a leaf node. And another terminology here is what is called a subtree. So if we take, a sub portion of the tree like this one, so this is called a subtree. This is actually called the subtree for node 4. So it's node 4 subtree. So if you take this highlighted part out, the root of that subtree is 4. Okay. And then there are some other terminologies, like what is a depth of a node. So if you take any node like this 3 here, so depth of a node is the number of edges from the node up to the root. So we need to count. So if somebody asks what is the depth of node 3, that means you have to count the number of edges. So here 1, 2 up to the root, right? So the depth of 3 is 2 here, because you have 2 edges between the 3 and the root node, which is 15. Okay. Root node has a depth of 0. So if you talk about root node, from root node to root node there are no edges, so because of that the depth is 0. Okay, so node 14 has the depth of 3. So if you take 14, yes, so quickly erase this. If you look at 14, you have 1, 2 and 3 edges. So because of that the depth is 3 for 14. Right? Node 18 has a depth of 2. Let's see. So node 18 is this guy. So we have 1 edge, 2 edges, right? So that is why the depth is 2. All right. Now another terminology that is used here is height of a node. So height of a node is the number of edges on the longest path from the node to a leaf. Right? So height of a node means that is the number of edges on the longest path from the node to the leaf. So previously depth is from the node to the root, height is from the node to the leaf, right? So if we take this example here, look, let's say 4. So the height of 4 is, you have to find out the most number of edges to a leaf. So here what I can see is, here we have two edges. Here if you take this path, it is 2 edges, this is 1 edge, this is 2 edges, right? So the maximum is 2 edges for node 4. For node 4 the maximum is 2 edges. So that is why the height of the node 4 is 2. Okay. And let's move on to leaf nodes. Leaf nodes have a height of 0. That is obvious, right? So 14 is a leaf node. It has a height of 0. Right? Just like how root has the depth of 0, the leaf nodes have the height of 0, because there's no other leaf from the leaf, right? The number of edges is 0. Okay, and then the height of a tree, so this previously we talked about height of a node. Here the height of a tree is the height of the root node. So what is meant by height of a tree is, you will have to find out the height of the root node. So start here, right? So you have to find out the maximum number of edges to the leaf, right? So here 1, 2, 3. So in any case the maximum is 3 to the leaf node. So because of that the height of this tree is 3. Okay, So how do we find out that? So start from the root and then count the edges. 1, 2, 3. 1, 2, right? And count the edges and take the maximum number of edges to the leaf node, right? Okay. And then we have something called levels of a tree. This is pretty simple. So levels of a tree is basically the root level is level 0, L0. And this is the second level, L1. This is the third level, L2. And this is the fourth level, L4. Right? So root is the level 0. Immediate children are the level 1. Grandchildren are level 2. And grandchildren are level 3. Right? And children are also called descendants. Right? So that's a technical term. So 4 is a child of 15, and then we call this a descendant. Right? A node is an ancestor of another node if it's in the node's path. So that's another technical term here, ancestor. Right? Ancestor. Ancestor is basically, now if you take this path here, right? So node 4 is an ancestor of node 7 as well as node 9 as well. Right? It should be in this line, right? So a node is an ancestor of another node if it's in the node's path. Right? Alright, so I hope you got that. And then, so we talked about the tree, the root node, what is an edge, what is a node, what is a leaf node, right? And then we talked about subtrees, right? And then we talked about depth of a node, we talked about height of a node, height of a tree, right? And then levels. Now we are moving into a new topic, which is binary tree. Now as you can see previously, here in this example, we have one node and then we have 3 children here, right? And then here there's only one child, and then here we have 3 children, here we have 2 children, right? So likewise. But here when it comes to binary tree, a binary tree is a data structure in which each node has at most 2 children. At most, that's the important bit. Each node has at most 2 children. So you can have 2 children. You can't have more than 2 children. So this is wrong. So this is a valid one. You can have 1 children, that is valid. You may not have any children. So that is also valid for a binary tree. Right? This is valid. So that is called a binary tree. And then there are only 2 children, one to the left and one to the right. Okay. So every node has 0, 1 or 2 children. So that is what I have mentioned here. So this one has no child, this one has only 1 child, this one has 2 child. So at most you can have 2 children. So children are referred to as the left child and the right child, right? So in this example, here this is like the parent node, and then you have a left child to your left, and this is the right child. So this is so if you have a tree like this is called the right child, and this is called the left child, right? And then when you move on, the binary tree is a data structure in which each node has at most 2 children, referred to as left and right child. So here this is also a binary tree, right? So this is valid because it has only one child. This is valid because it has only one child. So this is one child. So 15 has two children, 4 has two children, and 18 has one child, right? So this is basically a binary tree. So in case if you had a third child like that, now this becomes this is not a binary tree if this happens. Okay, so we will have to have at most, for each node we have at most 2 children. And then binary trees have some variations or definitions depending on its characteristic. We have something called a complete binary tree. So here it says all levels are completely filled. So all levels means we have this level 1, level 2, and level, so L0, L1, and L2. So here it says all levels are completely filled except possibly the last level. So the last level is this guy, right? So here it's not complete. So this level is complete because it's only the root, and then on the second level you have to have 2 child, so that is also complete. And on the L2 level you have from left to right you are filling it in, right? From left to right you are filling it in, but the last here we have a missing element, right? But that is fine, it doesn't matter. This is called a complete binary tree, right? And then there's something called a full binary tree. So this is every node has either 0 or 2 children. So every node has either 2 or 0 children. So that means if any of the node has only one child, that is not a full binary tree. Okay, what this means is actually, so you have a root node, right? And then you have here it's completed, right? So the level 1 is level 0 is completed, level 1 is completed because it has 2 children, and level 3 also is completed, right? So it has, for each node you have 2, right? So in the previous one this guy was missing, right? So that is when it was a complete binary tree, because when you fill from left to right it's not completing the whole thing, but it is called a complete binary tree. But full binary trees you can have either 0, that is those are leaf nodes, 0 children, or you should have 2 children. So these are all having 2 children, right? Okay. All right. So okay, so we have something called when a binary tree is not a complete binary tree, when binary tree is not a complete binary tree, we call it a incomplete binary tree, right? So this means, as you can see now, this level is okay, this level is okay, but this level you are missing a bit, right? So that means it's not filled from left to right. So when you come from left to right like this, it has to fill in order. So this has to fill, and then only this will have to fill, and this comes. Similarly on the level, so now this is L0, this is L1, this is L2, and then here we have an L3. L3 also, this guy has to start with here, but after completing the level above. Okay, so level completion will go like that, right? Each level has to be completed from left to right. Okay, so this is 1, this has 2, and this is 4, and this is 8 nodes, I mean. Okay, So this is called an incomplete binary tree when you don't have a complete binary tree. All right. So we are moving into a very important topic here. The binary tree will only have 2 children at most, and there's a special case here, something called a binary search tree, BST. We call this as an acronym for this, BST, binary search tree. So a binary tree where the left child contains values smaller than the parent node. Left child contains values smaller than the parent node, and the right child contains values greater than the parent node. So what this means is, in a binary search tree, whenever you take a node, to the left, when you see, it should be, now 20 should be less than 25. So left child should be less than the parent, and the right child should be greater than the parent, right? So even if you take this 20 to the left, you see 15, right? So that is less than 20, and what you see to the right is greater than 20, which is 22, right? So this property holds for each node. So here 27, left is less than 27, which is 26, right is greater than 27, which is 30, right? As you can see, it's the it holds those properties, right? Okay, so it's basically, if I reiterate this, a binary search tree is a binary tree where the left child contains values smaller than the parent node, and the right child contains values greater than the parent node, right? Simple as that. Okay, so there are few important bits regarding binary search tree. Can perform insertions, deletions, and retrievals in O log n time. So O log n is basically when you have hierarchy, right? You can divide the number of steps. Instead of going through all of the nodes, you can basically in each level it will what you have to search will get divided to half. So you'll understand this when we do an example. So the left child always has a smaller value than its parent. The right child always has a larger value than its parent. This means everything to the left of the root. So everything to the left of the root, so this whole thing to the left of the root is less than the value of the root. So as you can see, the root value is 25, right? So all of these guys are less than 25. All of the other guys, these guys, they are greater than 25. Right? So the left subtree is less than 25. The right subtree is greater than 25. Right? Basically greater than the root. Okay. So, and everything to the right of the root is greater than the value of the root. So that's what we explained there. So because of that, we can do a binary search. Okay, so binary search, what binary search means is, okay, if I want to search for example, 30, right? In this tree, I would come here, compare the values, 25, okay, root is 25, I want to search for 30. So because of that, I will not go to the left, I will go to the right, because our search value is 30. I know it is greater than 25. Because of that, it will be in the right subtree, right? It will go here, it will check with 27. Okay, 30 is greater than 27. So because of that, it will not go there. It will not go to the left subtree. it will go to the right subtree, right? And then it will check with this value to this value. Okay, 30 is equal to 30, and then it will find, right? It's a match here. So as you can see, with 1, 2, 3 comparisons, you are matching that, right? So if it was linear, you'll have to go from 1, 2, 3, 4, 5, 6, probably 6, 7 comparisons, right? But in binary tree, because you have a sorted order, and then left subtrees are less than the parent and the right subtree is greater than the parent, we can have some logic to go and find it first. Okay, so that is what we call the binary search, right? Here here's an example given, right? So we'll have to use this as input and create the binary search tree, right? So look at this very carefully. It's a pretty simple simple theory that we have to perform here. So the 25 is given, right? The first item is the root, so this guy is the root, right? And then 20 comes in. So just think, 20 comes in, where should it go? Should it go to the left or should it go to the right? So 20 is less than 25, because of that it will go to the left, and we'll place it there. And we take the 15. So 15 comes in, where should 15 go? So it is less than 25, it goes here. Less than 20, it goes to the left, right? And then 27. So 27 comes here, right? And because it's greater, it will go to the right side. And 30 comes here, it's greater than 25, it comes here, greater than 27, and it will be placed here, 30, right? So that is done. And 29 comes here, it is greater, it will go here, it will go here, it will not go there, right? Because it will go here, right? Because 29 is greater than 27, but when it compared with 30, 29 is less than 30, because of that it will be placed here as the left child of 30, right? And then we have 26. So 26 comes here, greater, so it will go here. 27 is greater than 26, so 26 should go to the left child, right? So 26 is less than 27, because of that it will be placed here in the left side. And then 22 comes here, okay? So 22 comes here, go to the left. 22 is greater than 20, so you should place it on the right side, right? And then 32 comes here, it's greater than 25, go to the right, greater than 27, go to the right, greater than 30, because of that it will be placed here. So here we go. So we have created the binary search tree based on this input, right? So that is how you do that. All right, so I hope we can apply the same logic to any input. Okay. All right, here is an example, right? When you are given this set of input, I'll just show how this happens. So we'll have to start with 25 as the root, and then the next one is 20, it should go to the left. Next one is 15 comes here, it's it's less than 25, goes there, again compares with 20, 15 is less than 20, so go to the left, right? And then 10 comes here, 10 comes here, okay. Now let's just do a different color. 10 comes here, it is less than 25, goes down, compares with 20, less than 20, goes down, compares with 15, 10 is compared with 15, 10 is less than 15, so it should end up here, right? So that's how this guy was created, right? All right, so as you can see, it's depending on the data we use, this tree might skew onto one side, right? And then we will later learn that there is something called balancing a tree, right? We should be able to balance this tree and probably get a better balanced tree. All right, so we come to the last bit. So this is basically duplicate value binary search tree. As you can see in previous examples, we did not have any duplicate values, right? So 25, 20. If we had like two 20s, so 20, the value 20 coming twice means it's a different story, right? And the implementation will depend on what rules you need to put in. So in some implementations it's not allowed. In some other implementations duplicate values are not allowed, right? If you want to store duplicates, decide on whether to store it in the left or right and stick with that. So say for example, in case if you want to cater for duplicates, cater for duplicate values, what you need to do is, say for example, this same thing, so 25, 20, 15, 27, 25, 20, 15, 27, and let's say you get a 20 again. So this is how it's been built, right? So here we have 25, 20, and then 15, and then 27, right? And then again 20. So 20 means you need to come here, right? And then go here, and 20 is equal to 20. That means if the rule says, if the rules we define says it should be stored as the right child, duplicates, so we say duplicates should be stored as right child. So if this was the rule, right, if this was the rule, then you will have to store it here like that, 20, okay? So you'll have to store it like this, 20, right? And then if it is left, so you come here, you'll see, okay, to the left you have some guy, right? And then what will happen is you'll have to rearrange this. So put 20 there and then put 15, something like that, right? So it depends, but most of the implementations, they do not allow the duplicates, right? All right, so another way to have a count, another way is to have a counter for each node. Say for example, 20, you had 20 on the first round, right? So node will contain like 25 and the counter as well. That's another variable, counter. So when there's another a second 20 comes in, the counter value will go to 2, right? So this counter is 1, we have 15 here, we have 27 there, and the last 20, it will come here, it will come there, and then increment to 2. The counter will be incremented to 2. So that is another way of handling duplicates. Okay, so with this, we have covered these important concepts of tree. So hopefully we will deep dive into the next topics regarding tree. So there are techniques of traversal, there are techniques of searching the tree, and then there are techniques of balancing the tree when the tree becomes imbalanced. Okay, so those will come next, and we'll stop it here. Okay, thank you very much.